full screen slide
I
there?
see it. I do see
Okay.
it.
Well, thanks for having me as a speaker. I feel like I'm in a very distinguished crowd here. I hope I don't get too intimidated. But I don't think it compared to I think it was 2014 conference. I was actually followed, my talk followed a Nobel Prize laureate, Joe Taylor. that was a little interesting. So my talk today is about the LoFASM project, and we're all looking at McMath-Hulbert Solar Observatory here in the Detroit area. We're looking into possible collaboration on data reduction on this LoFASM project. So anyway, LoFASM is the low frequency all sky monitor, and it uses 12 of these dual dipole low frequency LWA antennas. The range, it uses 12 altogether. The frequency range is 10 to 88 megahertz. Antennas and front-end electronics were originally developed for the long wavelength array by the U.S. Naval Research Lab, University of New Mexico, Virginia Tech, and Jet Propulsion Laboratory. So the LoFASM station is 12 antennas, and here I have a view of the very first one that was developed at the University of Texas, Rio Grande Valley, way down at the bottom of Texas. UGRTV is located in Brownsville, I believe, and the Port Mansfield site where the first antenna is about 60 miles away. You can see the site right down here. This is near the Port Mansfield Airport. So here's the site down here, and then here's the equipment shelter here about 1,000 feet away. Now, another one of these that's being built is being built at Hillsdale College, and that's about two hours away from McMath-Hulbert in southern Michigan. Here's a picture of their array. This is the standard 12 antenna setup, and excuse me, see a bit more vegetation around the site here in Michigan as compared to the one in Texas. The overhead view shows the array. It's sort of a Star of David arrangement, and that was done for certain beamforming reasons. The active developer there at Hillsdale is Dr. Tim Dolch. He's a physics professor. It was built with all private money. These systems run around $50,000 each. So it might be interesting for a smaller organization like one of our organizations that we're affiliated with to build. The reason for building this system is that it's intended to be used for transient studies. Everybody knows, I think, pretty much that transient studies are becoming a priority in astronomy these days, with things like fast radio bursts, gamma ray bursts, gravity waves, and so on. These are all very transient events. And in the optical world, we have a number of projects going. The Sloan Digital Sky Survey, for example, I believe was referenced in Dr. keynote speaker. Sorry, the name escapes me. Featuring that. Then there's the Pan-STARRS telescope. That's also coming online. That one will be in Hawaii, I believe. Other optical arrays are the Meerlicht, came on board in 2018 in South Africa. Robotic telescope located near Cape Town. And then this Observatory will be synchronized up with the new MeerKAT 64-dish array. So hopefully with all these systems working together, we may be able to capture more transients, including things like supernova, gamma ray bursts, fast radio bursts, gravity waves, and so on. So right now, there are 5 installations of LoFASM across the United States. The first one was in Port Mansfield, Texas. The original station went in about 2015, I believe. There's one out in the VLA in New Mexico. There's another one at Goldstone Station in California. Fourth one is at the Green Bank Observatory in West Virginia. I was hoping to see some of these this year, but of course, VLA conference got canceled and Green Bank is canceled. And then the fifth one, and the most recent one, was built by Tim Dolch at Hillsdale College in Hillsdale, Michigan. And Dr. Dolch invited us, McMath-Hulbert and SARA, to participate in this project. Ken Redcap and I are both volunteers at McMath-Hulbert, and so I think through that association, he kind of associates McMath-Hulbert with SARA, and I'm interested in pitching this as a citizen science project to SARA. It's fairly preliminary right now, but we'll see what happens. The stations are distributed geographically for RFI reasons, mostly. So if one station, of course, gets RFI, the other 4 most likely will not be affected by it, and then that data can be eliminated. The data from the sites could be used to create a gigantic interferometer at these low frequencies. And the interferometer configuration allows many small radio telescopes to be linked together to synthesize a much larger aperture telescope, as we saw in the last presentation. So the antenna is the original, basically design done for the long wavelength array. The first one being the VLA installation, 10 to 88 megahertz. So I believe they've got at least 2 of these LWA stations going now in New Mexico. I'm not aware of any more than that. LoFASM, primary goals will be low frequency radio transients and using field programmable gate array technology to implement a real full-time Stokes spectrometer and data recorder. The original array, many of us have seen this down at VLA, is this field of 256 antennas sitting off a little bit to the south of the hangar building over there, where they actually bring the VLA telescopes in and work on them. 256 of these cross dipole antennas, and the second station of this system is located about 75 kilometers northwest in the Savalita Wildlife Refuge. So I've got a movie here that that was made with the long wavelength array. Just shows the capability. Is everybody seeing this now or not?
Yes, we see it.
Oh, okay. Thank you. Oops.
Seeing the movie.
Try this again. Okay, here is, this is from the LWA array. It's called, their site is called LWA TV. And this is a real-time image of.
Hi, Tom. We're not seeing actually the movie.
Oh, you're not? Okay.
No. Okay.
I was seeing the slide, not the movie.
Yeah, I see the slide. Yeah.
Okay, hang on. Sorry. I have to go back and change my share, I guess. Okay.
While he's doing that, and I got a, let's see, John McElroy, I was just sitting there almost belly laughing over that. We said we should hook up playgrounds everywhere into a huge array. So that was really good. And John Colt, Q for later, what is the electrical circuit for the cross dipoles? The two questions there. So
yeah, that's coming.
All right.
Well, I guess we'll just skip that part. We'll go back to my presentation here.
Oh, that's too bad. All right. All right, your presentation's back? Yep.
Okay, thank you. Yeah, maybe I can get that going later. I've got another demo too that I guess I'm a little worried about. Anyway, here's the electronics, the front end electronics. We have very simple again, and Whit Reed actually sells these kits. So we have people involved in SARA involved with marketing and building and marketing these things, I understand. So we have, this is basically half the circuit here. We have a hybrid combiner and low pass filter gain, voltage regulator. And so we have a total gain of around 36 dB, noise figure 2.75 dB. It's not super, but then again, at this frequency range, you have quite a bit of noise from the galaxy already. So as I understand it, that's not a big problem so much. Here is another view of it. Then here's another view of the better view of the PCB. You can see the various components, and then the antenna connection points are these four pads out here. And so again, it's a fairly low cost setup. I think they retail for around $1,200 or so from what I recall. So the 12 antenna array at 20 megahertz has a beam pattern that looks like this. It's pointing straight up with very low gain off to the horizon, which of course is where most of your RFI comes from. It comes from, horizontally across from various sources on the ground. Red is the highest sensitivity and blue is the weakest. The double ring configuration, we have six rings, 6 antennas on the inner ring, and 6 antennas on the outer ring. Oh, sorry, I need to go back here. When added together in phase, the region of maximum sensitivity is directly overhead. When added 180 degrees out of phase, the array is most sensitive to signals from the horizon, which of course we don't want. So in the software, we can manipulate this to get the beam pattern to what we need, which in most cases straight up, although I suppose the beam could be tilted if you wanted to follow Jupiter or something like that. I don't know. So anyway, we have here the inner ring and the outer ring, and the radius ratio was set up such that we have 441 centimeters radius on the inner ring and 763.83. Detailed information on how this was done is found in a paper. I believe I referenced it at the back of my paper. So from these 12 antennas, we have 24 signals coming in. We have the outer antennas, east-west polarization, north-south polarization, and then the inners, east-west and north-south polarization. These are combined in a combiner that sits out basically in the middle of the 12 antenna array to come up with an outer east-west polarization, outer ring north-south polarization, inner ring east-west, inner ring north-south polarization. So we have these 4 signals coming out from our 12 antennas, and then these 4 cables run back to the equipment shack, which is several hundred meters or 1,000 feet away typically. Then in the equipment shack, we have the 4 signals come in over low-loss coax to the analog receiver board, the ARX board. We have buffered and filtered analog. Then we have a Roach board, which is a kind of off-the-shelf signal processing board right now. It comes from the University of California, I believe. Rubidium time base, synchronized by GPS for time sync, a good time synchronization. The output of the Roach board, which stands for Reconfigurable Open Architecture Computing Hardware, goes over 10 gigabit per second internet to the Linux PC for logging and uploading data, and then that goes to the internet. So basically this thing runs 24/7, or that's the intent, and it generates about 33 gigabytes of data per day that has to be uploaded to a central location. Let's see, here inside the Roach board, we have our 4 incoming signals. We sample at 200 megasamples per second. So we get our time domain signals, perform the Fourier transform. So we have frequency domain signals now, outer east, outer west, inner west. The correlator comes up with 10 correlated signals. So this is how the beamform is controlled, as I understand it again. We have autocorrelation signals of each one against itself. And then we have the 6 remaining cross-correlation signals. And then this goes over gigabit Ethernet to the processing and logging PC. What the full Stokes spectrometer claim means, as I understand it, again, I'm just learning all this myself. Basically, it means that the signals from each of the individual dipoles are combined in phase to synthesize the beam. The desired beam shape is to the vertical with minimal horizontal lobes. The 100 megahertz correlating spectrometer is using the Roach board, and again, the sample rate is 200 megasamples per second. A little bit about correlators for those of us who are not so familiar with all this. The correlation is a digital device that takes the Nyquist sample digital streams and basically it multiplies them with an appropriate time lag as desired. It can be programmed in. The correlators are basically the heart of all radio astronomy telescopes today, and especially with interferometry. It's a very, very significant process. The definition of cross correlation here is from the textbook definition we have. It's a time that it's done over time domain, and then that converts it to frequency domain. So we can this is a two-way transformation. We can transform from time to frequency or frequency back to time for good signal processing. Autocorrelation is the same process, only you beat the two the signal against itself, and then this comes up with the frequency domain power spectrum again, as I understand it. The Roach board looks something like this, and it's an off-the-shelf signal processing unit from Berkeley Wireless Research Center. Xilinx field programmable gate array. I believe this system uses the Roach 1 board, which is probably not so state-of-the-art anymore, but it's more than adequate for the these purposes at these low frequencies. So here's some output that I guess Professor Dolch detected at Hillsdale. Here's an interesting one. You look at it and eventually you realize that this must be a man-made signal of some kind, because it apparently has a very strong carrier signal with fluctuating sidebands off to the higher frequency range. This is looks like it was done over maybe half an hour or more, maybe 40 minutes, something like that. So data looks like possibly a digital TV signal, but the closest digital signal in this frequency range would be channel 2. The pilot is at 54 megahertz, 0.3 megahertz. So that's probably not what it is. It could be a military, excuse me, a military signal or something else. They've been over the horizon radar, 30 minutes duration. The lower diagram is a 5-minute event. So anyway, there is a possible transient. To my knowledge, they haven't detected any natural or astronomical transients. So anyway, Dr. Dolch has kindly provided data on his Google Drive for us. The files come out in compressed form, and the date and time of the file is keyed in the file name, so we have the date and time here. So these compressed files, these are 5-minute intervals here. Looks like the latest data that he has uploaded was back in March of this year. These are about 34 megabytes. And so for a whole day, there would be 288 files available for the whole day's observation record. And so we're looking at ways to handle this and actually go through this data manually and look for transients. I'm not aware if anybody's doing this yet. So, okay, here we go again. I'm going to try to do a live demo using the tools that are provided. So I'm going to stop screen sharing. And then I'm going to share, let's see. So Louis D'Artes, is everybody seeing my Linux terminal window here? Rich?
Yeah, we see it, Tom.
Okay, good. So what I want to do is I want to explain a little bit about these tools that are available on D'Artes's GitHub site, and these tools take the raw data files that we have available and creates graphic displays. I'm going to go in here and pull up this first one here. Takes a little bit of time. Okay, is everybody seeing this animated display? Apparently not.
No.
Okay. I've got a see it now?
Yeah, oh yeah.
Okay, so what this tool does is it scans through the all of the 10 output files and does an animation. This is a 5-minute animation, and it looks something like this. So I mean, something like this could actually be, I'm thinking, could be used by a student to look at all 12 or 10 files and possibly note a transient event. Now there's another tool that lets us look at the data for one correlation. And I'll have to share it again. Okay, so this is I guess, I believe it's one, yeah, it's one correlation. It's the autocorrelation from one of the polarizations. And this view allows you to view the data over time. So you can actually look at each one of these sweeps for a transient. Again, I think if we could provide these to students in some kind of an organized fashion so they could actually go up and daily go through these, I think it'd be a very fun citizen science project. And I'm hoping maybe I can catch some interest from, excuse me, some interest from SARA too, to do something like this. I think it might be a worthwhile thing. Back to the presentation here. Oops.
Can you go back to that original picture?
Which
one?
one?
Trying to get the one that you were trying to get the real data. Now that you know how to do it.
Oh, okay. Let me share that again.
I got two questions while you're doing that.
Yeah.
Ground preparation for the antenna.
Right.
And what is the cost of a roach board?
Roach board is around 10,000, as I recall. So that's a fair amount. Okay, I messed up here. Can't find my... Oh, here it is. This one you're looking for?
Oh no, the one that the original one that you were trying to get on. I think it shows the.
Yeah. Okay.
Yeah.
That one. Yeah. Now that I know how to do it. Hang on. Okay, now. Hey, bear with me for just a second here. Okay, here we go. Ready to see that? Yes? No?
There you go. Yes.
See it? Okay.
Yep.
So here's an output from the LWA array down in Socorro at the VLA. And this one's pretty neat. This one was done at, looks like 25.6 megahertz or so. And the neat thing about it is they happen to catch a Jupiter storm event down here. If you watch Jupiter, you see Jupiter flashing. Let me run that back a little bit. There's Jupiter flashing. Does everybody see that? So with this 256 antenna array at 25 megahertz, this is the kind of resolution you can get. But the plan, I guess, is to build a bunch more of these stations around. So we should, in the future, we should see pretty decent resolution at these low frequencies. This little noise spike up here, I believe, is RFI, possibly from an overhead power line in the area. So the LWA, you had a question about the grounding, did I hear?
Ground preparation for the antenna.
Yeah, it uses a it uses a galvanized screen, and the idea there is to stabilize the impedance. I think I did mention something in my presentation. So once I get back to that, I think we'll take a look there.
Another question, can you set up your own LWA TV using Raspberry Pi?
I don't think that's possible, is it?
Well, let's see. Whit sent this. He's even sent a link.
Okay, so it is possible. Okay, I guess we're back to the presentation now. Here's, again, just a rehash of this animation that you can use to look for. And the other one, the BBX, Explore BBX 2D.py program. Again, these are tools that you can easily download and install from the GitHub site. I'm running this on Windows subsystem for Linux. I'm not running dual boot or anything like that. And it seems to work pretty well. I had a little bit of trouble with getting to connect to my Windows server. It's use a tool, an X server tool in Linux, and you fiddle around with it and you can get it to go eventually. So anyway, what I would like to do, or what I'm looking into, is to come up with a way for students to view this data and then manually look for transient events. To my knowledge, they're generating all this data, and I'm not sure if anybody is really looking that closely yet. So maybe this is a way that we could jump in and actually get some underprivileged students in the area involved, doing a little bit of astronomical work. A little bit about the McMath-Hulbert Observatory, where Redcap and I are volunteers and officers actually on the board. Also, this was established as a solar observatory in 1930 by a group of rather rich, wealthy amateur astronomers. They did pioneering work, movie work on astronomical events. They actually made movies of Jupiter's moons in orbit, shadows changing on the moon. They have caught the interest of the University of Michigan here in the area, and they were challenged to make some movies of solar events, and they actually built themselves a scanning solar spectroheliograph, and they put it in this first tower here. This is actually the first one built. These remaining towers were built over the next 5 to 10 years. This one was, Tower 2 is 1935, the tallest one, 1940. So anyway, it was in operation by the University of Michigan up to about 1979. It went into private ownership. It's on its second owner now. And he's getting to the point where he really wants us to do something with it. So we're looking at a significant, fundraising effort to actually preserve the place and maybe improve it. But of course, we need to have some sort of reason and to preserve it. And we're looking into STEM type projects, science type education projects with maybe underprivileged but deserving children. So what I'm thinking about is, since the McMath-Hulbert Observatory is near Pontiac, Michigan, which is a low-income area, it gives us this opportunity to serve underprivileged students. Possibly we could set up a Galaxy Zoo type project with people set up to download the files and look for transients in the data. I would be interested in talking to SARA leadership if SARA would be interested in collaborating with such a project. And even building a LoFASM array isn't that bad. It's relatively low cost, about $50,000 for 12 antenna setup. So even maybe a school district, a very motivated school district, could actually build one of these things. I guess that's about it for now. So anyway, the LoFASM system is designed to detect fast radio transients in the 10 to 80 megahertz range. System is low cost. Smaller organizations could build a station. Ideally, when it's up and running, full function, we have 12 long wavelength array antennas with 24/7 watch on the skies. Geographically separated stations will eliminate false local RFI events. Data uploaded to a central location. Tools have been developed, which I think we could actually use right now to allow users to create graphical output and actually look for transients. And I think this project could make a great citizen science project if it were organized properly and managed properly. Thank you.
Okay, any questions? All right, I don't see any more questions on here. And that question about the LWA TV was not a question, it was a statement by Whitman. Got very good, Tom. Thanks, Whit. Let's see, great presentation from Step. Thanks, Tom. Great presentation. Perhaps NSF may have a grant for the education program idea. Bruce Randall, on CAS A and SIG A, they were flickering. Why?
Most likely that's atmospheric, an atmospheric effect. You know what HF is like for communications, Bruce. So probably that's transparency changes in the ionosphere would be my guess.
Okay. All right. Are the dimensions of the antenna published anywhere?
Yeah, these specs are all online. The circuit is online, available. So, and if you don't want to build your own, I believe Whit would be happy to sell you one.
Yeah. All right. Okay, I think that's it. Thank you very much. Outstanding brief.